Hello, welcome to our third video on optimization. In this video, we're going to take a look at a challenging problem, the problem of carrying a pipe around a corner. So here's the setting. You want to carry a long pipe, holding it horizontally. You want to carry it down a hall of width A feet. At the end of the hall is a right angle turn onto another hall of width B feet. And you've all done this before, tried to carry long things down halls around corners. If the pole is, or the pipe is too long, you'll not be able to get around the corner. So you want to find the length of the longest pipe that can be carried horizontally and maneuvered around the corner. So here's a picture of the situation as we see it. So at some point this pipe's going to have to maneuver around the corner, so it's going to have to make this turn like this. Something like that, so you can kind of imagine how this might maneuver as it turns around the corner. I think you can see from these sample segments here that for some of these you'd be stuck, and for example if you got in this position it's clear that the pole is not going to move anymore. You can't get any movement that way or that way on the two ends of the pole, so it would be stuck. So that pole might be too long to get around the corner. Of course, the challenge here is getting the pipe around the corner, and as we saw in these illustrations, if the pipe is too long, say something like this, you can start to maneuver on the corner, pivot on this corner, but this pipe would get stuck. You can kind of imagine that you could not move this end up and this end to the right at the same time. So what's kind of interesting about this problem is that though we state it as a find the longest, so it sounds like a maximum problem, it really is a problem of minimization, because the longest pipe that will fit around the corner is the shortest pipe that extends from wall A to wall B and hits the corner at C. So if we go back to our pictures here, right here in red we might see, perhaps this is that shortest distance that again goes from wall A to wall B and tangent at the corner. And you can imagine that if you had some longer pipe, something like this, if it's shorter than that shortest red distance, that pipe is not going to make it around the corner. This one, the red one, you just might have enough room to maneuver, but the blue one in this case, no. So to make this work, we're going to have to find something we have over which we have control to help us measure this. So let's imagine we have a pipe here extending from wall A to wall B and hitting the corner at C, much like this. We're going to use as our variable this angle theta that the pipe makes with the horizontal in the hall. Now, you might try this afterwards with another variable. You can also label this vertical edge here length x and work from that, but we're going to work with this variable theta instead to give us some practice with trigonometry. And we're going to actually work with the two separate lengths, L1 and L2, which are the lengths of the pipe from wall A to C, and then from C over to wall B. So we've labeled these things on the diagram here. You see the angle theta, and of course the theta occurs two places by similar triangles, and the fact that these A and this wall from C, those two things are parallel. And so this transversal is going to cut those parallels at equal angles. So those are both going to be the angle theta. We've labeled the L1 and the L2. So those two right triangles are similar. They're both right triangles, and they share an angle. And so we're going to use some trigonometry. In the lower triangle first, we can think of the adjacent side down here over the hypotenuse. A over L1 is cosine theta. We can solve this equation for L1 to get L1 equals A over cosine theta or A secant theta. Moving up to the upper triangle, we then know about B, so we want to think about B over L2. That's going to be the sine of theta. And so L2 will be B over sine theta or B cosecant theta. So we now have the lengths of the two pieces into which the pipe is divided by that point C. So the length of the pipe in this position is given by the sum of L1 and L2. So this is A secant theta plus B cosecant theta. And we have restrictions on the theta here. The theta is going to be something between 0 and pi over 2. You can imagine that an angle of 0 would put our pipe in some position something like this. So there might be a very small angle here, but the angle could never be 0. Otherwise, the pipe would be infinitely long, just extending down this wall. And likewise, we're not going to have an angle of a right angle, pi over 2 here. If that was the case, the pipe would be infinitely long and just extending up this way. Furthermore, of course, cosecant and secant, one is not defined at 0, the other not defined at pi, so we're going to end up working on this open interval from 0 to pi over 2 here. So remember, we want to minimize this expression. We want to find the shortest distance that goes from wall A to C to wall B. So we want to minimize the expression for L, which was A secant theta plus B cosecant theta, where theta is allowed to range from 0 to pi over 2. So this function is differentiable on the open interval we're looking at. So we can find the critical points first by setting this derivative equal to 0. So going back to our differentiation formulas, the derivative of secant is secant times tangent, and the derivative of cosecant is minus cosecant times cotangent. So there is our derivative of L with respect to theta. And do a little work with this. If we convert things to sines and cosines, the secant is 1 over cosine, the tangent is sine over cosine. The first expression gives that. And likewise, cotangent over cosecant becomes cosine over sine squared. In the last line, we've added these two fractions. So we've multiplied the top and bottom of this first fraction by sine squared theta over sine squared theta. That gives us a denominator of cosine squared sine squared. And in this one, we've multiplied top and bottom by cosine squared theta over cosine squared theta. That gave us sine cubed times a in the numerator of the left fraction and b times cosine cubed theta in the numerator of the right fraction. And so this is our present expression for that derivative. And for critical points, we want to set the derivative to 0. And of course, this derivative, we've now written it as a fraction. We've converted to sines and cosines, since we're probably a little more familiar with those. And this expression is going to be 0 only if its numerator is 0. So it's enough to think about this numerator up here being 0. And we can manipulate that to find b over a is equal to sine cubed theta over cosine cubed theta, which simplifies to tangent cubed theta. So not too hard to solve for theta there if we want. So taking cube roots, we get the tangent of theta is the cube root of b over a. That'll be some positive number. And then the angle itself, so it has to be between 0 and pi over 2, is going to be given by the inverse tangent of cube root of b over a. Remember, inverse tangent gives an angle between minus pi over 2 and pi over 2. And of course, the angle in our problem is between 0 and pi over 2, so inverse tangent does this for us. And so this is the only critical point in the interval from 0 to pi over 2. So before we go on and work with this critical value to find out what the corresponding length of the pipe is, we want to make sure this corresponds to the minimum we are seeking. So we're going to do this by looking at the intervals of our 0 to pi over 2 interval, looking at the subintervals on which this function is increasing or decreasing. So let's consider this first derivative again, as we see right here. And so our goal here is this. We have this interval that goes from 0 to pi over 2, open dots because those are not in the points to be considered. And we have this number c, the critical value, which is this inverse tangent of the cube root of b over a. So we're first of all going to think about this left interval between 0 and c. And for that, I'm going to imagine that we have a theta that is very close to 0 down here. It's not going to equal 0, but I can make it as close as I want because I just want to see what happens to one point in this interval. what happens to the derivative at that point. So if I pick a theta very close to 0, then the sine of theta will be close to 0, and the cosine theta will be close to 1. And if the sine is 0 and the cosine is close to 1, we can see we're going to get a negative numerator up there, and that'll tell us that the derivative is negative. L prime of theta is less than 0 here, and so on this interval, L is going to be decreasing. We'll do a similar analysis for the right-hand side by taking a theta close to pi over 2, because for that, the sine will be close to 1, and the cosine will be close to 0, and we'll see that L prime of theta is bigger than 0 at that side. So let's go ahead and take a look at that, and here it is. So with theta very close to pi over 2, and still between c and pi over 2, here's our situation once again, 0, pi over 2, and c. We already showed L is decreasing over here, so we take our theta way over here, close to pi over 2, and we can see that we get a positive numerator in this case, so that means that the derivative is positive, and hence the function L is going to be increasing on this interval. Okay. And in fact, if you were to graph this L expression on the interval, if you were to look at the graph of L, I guess I'll just have to do it right here. Here's 0, and here's pi over 2. Here's the critical point C. If you graph this, you'll actually see vertical asymptotes at 0 and at pi over 2. And again, the function decreasing to the left of the critical point, increasing to the right. So that's enough to tell us that this critical point really does correspond to the minimum of this function on the interval. Okay. It's a low point, and it has to be the low point because of the geometry of the function. So we know this critical point corresponds to a minimum value for the expression L on this interval of concern from 0 to pi over 2. So to complete the problem, we just have to find the length of the pipe that corresponds to this minimum length. And that's just a little bit more trigonometry. So we're going to bring the picture back. Here's the picture from which we were working. And we now know some information about theta. The theta is the inverse tangent of the cube root of b over a. Or, which will be easier for our purposes, we know that for the minimum, this tangent theta is equal to the cube root of b over a. So we're going to go back to these two right triangles, and now we're going to start by finding these other legs of the triangles, y and x, and then use the Pythagorean theorem to find L1 and L2, and then add those values to get the length of the pipe. So from the two triangles in the figure, let's work with the lower one first. Well, in fact, both at once, I guess. We have the cube root of b over a is the tangent of theta. And from the lower triangle, the tangent is opposite over adjacent, so that's y over a. And in the upper triangle, that opposite over adjacent becomes b over x. So there's two expressions for tangent theta. We can then solve the equation for y and for x, and the y is a little easier, so let's take a look at that first. So we take a look at that equation, multiply both sides by a. We find y is a times the cube root of b over a. We're going to write this b over a cube root as b to the 1/3 over a to the 1/3. And then a divided by a to the 1/3 gives the a to the 2/3 you see here. For x, it's very similar. We have to do a little bit with reciprocals here, but the x is going to be b times the cube root of a over b. Some nice symmetry there. And by similar algebra with the 1/3 powers, this becomes a to the 1/3 times b to the 2/3. So back here in this picture, we now know the side A of this lower triangle and the side Y. We know the side X of the upper triangle and the side B. And because we have right triangles, we can use the Pythagorean theorem. Let's start with L1 first. So L1, working with this triangle, is going to be the square root of a squared plus y squared. And we have the value for y up here. Y is a to the 2/3, b to the 1/3. So we replace y by that expression and square it. And then we're going to have an a to the 2/3 squared, which you're going to pull under the radical. Now that a to the 2/3 squared becomes a to the 4/3. And if I factor an a to the 4/3 out of that one also, that a squared, we're left with a to the 2/3 in the a squared. So a little algebra, verify this, make sure you understand this, but this turns out to give us L1 as being a to the 2/3 times the square root of a to the 2/3, b to the 2/3. And for L2, very similar. L2 will be the square root of x squared plus b squared. And we'll just put in this value for x, the a to the 1/3, b to the 2/3, and do similar algebra to find L2 turns out to be that. So get out your paper, make sure you can work through this algebra of exponents to verify L1 and L2 do turn out as we have there. So we're just about done. We want the length of that pipe of minimal length that goes from wall A to corner C to wall B. And now that we know the length of the two smaller pieces, L1 and L2, it's just a matter of adding those, as we've done down here. And so the pipe of maximal length that can be carried horizontally around the corner, okay, that maximum pipe again is the length of the minimal segment that extends from wall A to the corner to wall B, and that's going to be given by that length L we just found, L1 plus L2. And so here we've added those two expressions we found for L1 and L2 over here. And they both have the square root of a to the 2/3, b to the 2/3 factor, so we can do a little factorization. And in fact, then we find really kind of a pleasing looking answer. The pipe, the longest pipe that can carry down the hall, has length of a to the 2/3 plus b to the 2/3 to the 3/2 power. And finally, units are important. Remember, a and b were in feet, so evidently this expression is going to be in feet also. Okay, so that concludes our last problem on optimization. Please read through the examples in the textbook and work some of these on your own and have fun with it. Bye.